Feature engineering. Coming up with features is difficult, time-consuming, requires expert knowledge. Applied machine learning, however, is basically feature engineering. So a classifier is a function model. Given structured data with labels L equals C1 to CR, those are the class names. Exploration gives us a data representation in a vector space. The feature space is script F, the set of all possible values of the features. They'll be engineered, and we'll see in this video. A classifier is then a function mapping the feature space, which is a subset of a vector space, to another vector space, the response vector space, given by this functional form, with weights as parameters. Even when we predict labels, that is, the labels are also mapped to numerical. For example, we may do, instead of C1 to CR, just the indexes 1 to R. Because predicting an index of I is the same as predicting a label of CI. But to avoid bias, we often one-hot encode the labels. In other words, the labels are also mapped to vectors. So C1 might go to 1 and then all zeros, up to CR is 0 zeros, all the way to the last one is a 1. For example, recall the iris data. So our feature space was our latent space. Our little f was the neighbor's predictions of unlabeled xy. Isotosa red, I versicolor is green, and I virginica is blue, and those correspond to the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1 respectively. Why? Because the order 0, 1, 2 is biased. We don't want the labels to have a bias that we introduce. So if we have more than 2 classes, then we need to do this, unless the classes truly are ordered. But for 2 labels, positives are 1, negatives are 0, and we don't have to worry about bias. So feature selection is basic feature engineering by comparing and correlating features to a target. Some features may not be necessary, some features may be misleading. Most algorithms also tend to have weighted versions. How do we choose the weights? Well, we estimate feature importance. Choosing weights also means we use cross-validation. How are the features interrelated? What's their topology? But feature selection is using less data to make high-quality predictions. But in general, more data beats better model. For example, in nearest neighbor methods, we saw these 2 examples. Notice that data from 100 games versus data from 200 games. We can't predict the decision boundary from only 100 games, but we can from 200 games. But there are multiple approaches to more data. More features, which leads to the curse of dimensionality. More classes, more responses, more observations, which leads to more confusion. So where do we get more data from? Well, more observations means somebody on your team, probably not you, is going to have to collect more data. Feature engineering nearly always requires domain knowledge, scientific or technical context. Feature engineering often uses domain knowledge to create and modify features so that algorithms work. If you're feature engineering in a physics application, somebody will need a physics background. In a financial application, somebody's going to need a finance background. Because algorithms are not scientists, and a set of big data tells many, many stories, but your application is only interested in one of those stories. We will avoid problems that require domain knowledge we don't have, but as a data scientist, you should expect to work closely with domain experts. More features often means creating new features from the given features. And this tends to have 3 steps. Not a hard and fast rule, but tend to do the following. Transforming the given features into new features, evaluation of the new features via metrics, and then comparison of models with and without the new features. There are infinitely many possibilities here, and many more than we could do in a single course that are used out there, but there are a few that are quite common. Means, moments, trends among existing features, and polynomial approximations of nonlinear transformations. So model comparison is feature assessment. It's not for finding a best model. All models are useful. In fact, we'll later on learn that the best model is always all the models. But better model implies that new features are useful. Model comparisons and metric assessments of new features is to avoid feature creation that only adds noise or bias to the data. There are two important methods in model comparison. Comparisons via metrics, especially the precision and recall metrics, and information criteria, adjusting performance measures to account for differing model complexities. But that'll have to wait till later. Usually, or at least very often, both are used in the same application. So why precision and recall and not receiver operating characteristic? Well, here are our metrics of recall and precision. And as conditional probabilities, recall is the probability that the prediction is positive given that the actual is positive. Whereas precision is the probability the actual is positive given that we know that the prediction is positive. In other words, precision is the likelihood of being positive in reality if predicted positive, a measure of a classifier's predictive ability, especially for the positives. Here is specificity, and remember the receiver operating characteristic was sensitivity versus 1 minus specificity. And it is the probability that prediction is negative given that the actual is negative. As fractions, given the definition of conditional probability, we have these three. If we have balanced data, the probability that the actual is positive is about the same as the probability that the actual is negative, and they're both about 1/2. And so notice that we're comparing these two joint probabilities when we're looking at the receiver operating characteristic. But for precision and recall, we have the actual positive probability distribution, the predictive positive distribution, and the joint positive distribution. So for balanced data, we often use the receiver operating characteristic in model comparisons, but precision and recall use more distribution information. Now, remember our extremely positive classifier? If all the observations are classified positive, then true positive is positive, false positive is negative, and recall is 1, precision is p over little m. M being the number of observations. If you have extremely negative, then P is 0 and TP is 0 and FP is 0. And precision is indeterminate because we would have a 0 over 0. So we look at a nearly negative classifier. Suppose that you have 1, and remember here M is very large, but you only have 1 positive prediction and it's correct. Then recall is 1 over P, which is approximately 0, P being very large, and precision is 1. So for a given binary classifier, little r denotes recall, little s denotes precision. The ideal is where precision and recall are both 1. And we get a point. If we're extremely positive, we get this P over M point over here on the far right. And if we're nearly negative, we're very close to the pink dot there on the upper left. So the precision recall curve is formed by connecting the points by line segments so that precision is a function of recall. Now we can also do this with a threshold. Here are our actual labels, and here is the probability that they are positive. And here are thresholds. So similar to the ROC curve, a classifier for each threshold t, the probability greater than t means you predict the observation is positive. And notice that t ranges across the thresholds. So that means we start with the extremely positive classifier and we'll end up at the nearly negative classifier. And as we move across, we will get a curve which is known as the precision recall curve. The best is best threshold is the one closest to the ideal. So the ideal would be to maintain precision equals 1 as the recall increases. So what would be really nice is if we simply stayed at that upper bound until almost at the very end. The closer the PRC gets to ideal, the better. The area under the precision recall curve is between 0 and 1. High area implies both high precision and high recall. We often combine this with the F1 score, the harmonic mean of precision and recall, and the closer to 1, the better. So let's look at two examples, and we're going to use these 3 steps. They're not hard and fast, but it tends to be what we do. There are so many possible examples that I could do, because engineering new features is what we data scientists do. It's what defines our field. But we're going to look at 2. We're going to look at exploration that leads to new features, and we're going to look at polynomial approximations of nonlinear transforms. So back to our calculus exams and calculus course data. Can we predict a pass from these features? Well, first thing we do is pre-process, rescale the features, and then once we've done that, there are some obvious new features: mean, standard deviation, skewness, kurtosis, the first 4 moments of the exams. Notice that these values are of the rescaled original data. Only mean correlates significantly with the target pass, but does it provide new information? You see, adding new features always adds more noise and always increases the risk of overfitting. The true test is how the new feature performs in a model. So here are some models, K and N with K equals 1 in logistic regression. And if you'll look at the legends, you'll see that when we add the mean, we get slightly better precision recall curve. If we used all 4 of the moments, we definitely would have a worst performance. Now, we also like to cluster to get more information. Given a data set, cluster it and include the cluster membership of the ith observation as a new feature. In essence, clustering creates a classifier. The response is the cluster label, but cluster label is also a new feature. Does it have any value? Well, we need cluster metrics. The first one is homogeneity. So an obvious classifier, a data set clusters into 2 components, one of all positives and the other of all negatives. Something like that. In this case, just the clustering itself is all we need to be our classifier. But it only worked because the data had a simple topology. There are 2 label homogeneous separate clusters. Homogeneity is a similarity score between actual labels and the labels predicted by clustering. The closer to 1, the more clustering corresponds to the classification labels. See, the clusters may be well defined, but the actual labels may not be related to the clusters, as we see in this example. And you'll see more examples in the notebooks. Now let's look at polynomial features. Given numerical features, x1 to xn, create powers and monomials, products of the variables, for all k equals 1 up to some maximum degree. This extends data into a higher dimensional context. Remember our very first module where we talked about classifiers and extending the higher dimensions to improve classification. This is one way of doing that. For example, our tunable binary data, that was our first video in Module 4. Data sampled uniformly randomly from 0, 1 cross 0, 1. xy is positive if cosine squared of pi nu x is less than y. In other words, if the point is above the curve, y equals cosine squared pi nu x, then we say it's positive. Negative if the point's below the curve. The training set will turn out to be about half positive and half negative. The testing set's about half positive and half negative. This is not linearly separable data, at least not in 2 dimensions. But what about in higher dimensions? So logistic regression is a linear separator. What if we just naively applied logistic regression to this data? Well, here we did it. And we have very poor accuracy, hardly better than just a coin toss classifier. Why? Because this data is not linearly separable. But if we somehow knew to transform the data with the transformation cosine squared pi nu x, then we would get linearly separable. So if we knew to do this transformation, we would get this data, and that is linearly separable. Now this is unfortunately the true model. We know it because we created this tunable binary data as a way of testing our classifiers. Yet whatever this true model is, there often are times we can assume it can be approximated by a high degree polynomial. So if we create polynomial features, monomials of x, and then we do the same logistic regression again, now notice our accuracy is 95%. Why? Because we've actually approximated the separator with a polynomial. If it was an analytic function, we would be then, say, approximating it with this Taylor polynomial. So linear and higher dimensions with additional features. But in our original setting, we get this kind of a decision surface. Why? Because that's what it looks like when we add these new features as polynomials. Now, often this doesn't work, and this is a very important point. You see, it's all feature engineering. Mathematically, the goal of feature engineering is to discover the topology of the process geometry that was sampled to produce the data being used. We're looking for structure. Clustering is a type of manifold learning. Manifold is a mathematical topology. Manifold learning is discover mathematical structure. Deep learning is machine learning that creates its own feature representations when it solves a problem. Generative AI builds and samples from those models feature representations. Now, so far we've only seen a few metrics. As the course continues, we'll add more metrics. Algorithms differ primarily in how they use the data available to them. Neural networks are an exception, I'll explain later. Metrics, therefore, are at the heart of data science. The ability to assess outcomes is at least as important as the ability to produce outcomes. A well-assessed, simple algorithm is often all you need. Metrics are also at the heart of feature engineering. So exploratory data analysis leads to new features. Metrics and models used to assess their data. Most new features are noise or bias. So just randomly creating new features is probably just going to create a big mess. We always need more and better data, but we have to extract information in how features are interrelated. And there's always more to the data than just the numbers. And most of your data science life is going to be spent doing feature engineering as part of a team working with domain experts. So one final note, data scientists often obtain a background in some specific domain, but even then, you should expect to work on teams with domain experts who are not experts in data science. That will be you on that team.